To fix the runtime exception, we will use the Microsoft Dependency Injection Container built into ASP.NET Core. The dependency injection container is configured when the application starts by registering services with it. We register application services with an iService collection. Any services that we expect to be injected at runtime must be registered with the iService collection. Failure to do so results in exceptions being thrown when those dependencies are first required, just as we saw in the example previously. In this demo, we'll register our first service with the dependency injection container. If you use ASP.NET Core 5 and prior templates, it's worth highlighting that you configure services inside a class named Startup within its Configure Services method. This approach is still supported if you've upgraded a project to ASP.NET Core 6 and want to continue using that pattern. We're focusing on ASP.NET Core 6 in this course. Services are registered within the program.cs file. This file uses the C#9 feature called top-level statements and is the entry point for the application. The builder pattern is used with a web application builder, providing access for us to configure ASP.NET Core with services and the request pipeline. To register services, we access the iService collection from the builder. I like to add a local variable to simplify my service registrations, which I'll name services, and this will provide a shortcut to the iService collection. We will register services with this iService collection. Various extension methods exist to support different registration scenarios. To get us started, we'll use this overload of the add_transient extension method, accepting two generic arguments. The first generic argument is the abstract type, known as the service type. This is the type that dependent classes can expect to be injected by including it in their constructor parameters. The second generic argument is the implementation type, which is constrained such that it must inherit from and implement the service type. This method registers a service with a transient lifetime. I'll discuss service lifetimes in much greater detail in the Microsoft Dependency Injection Container module coming up. Until we fully understand the pros and cons of the different lifetimes, transient is a safe default for us to choose. The order of service registrations is generally not important. They can occur anywhere before build is called on the web application builder. One situation where order should be considered is if you find yourself registering multiple implementations of an interface. Now, we'll discuss this scenario in much more detail in the module called Registering More Complex Services. I prefer to register my application services before the framework and third-party services, so they're more visible at the beginning of the file. Let's register a service for the iWeather Forecaster interface. This is the type that we added to the index model constructor parameters. The implementation type in this case is going to be the concrete random weather forecaster type. The container will attempt to create and return an instance of this type when resolving a request for the iWeather Forecaster service type. This single line is all that's required to register a service, so we can go ahead and rerun the application. This time, no exception is thrown and the home page loads correctly. ASP.NET Core has activated the index model by resolving the required dependency from within the dependency injection container. I can hit F5 here to refresh this page several times, and each time the random weather forecaster returns a new random weather result. In addition to injecting services for types we define, we can also inject services provided by the ASP.NET Core framework. Logging is one such service available in ASP.NET Core, which many applications take advantage of to support diagnosing application errors at runtime. In this demo, we'll inject a logging service into the index model. Just as we can inject our own services into the page model constructor, we can inject framework dependencies. We'll accept a generic iLogger for the index model type as the second parameter of the constructor. This allows us to log messages where the source can be attributed to this type. We'll name this parameter logger and use the Visual Studio tooling to generate and assign a local field, just as we did earlier on. At the bottom of the onGet method, we have a catch block for any errors that occur when loading the weather forecast. We can access the logger from the private field and write out an error message should this occur. We don't need to register anything ourselves for logging to function, because logging services are registered as part of the ASP.NET Core hosting framework. We can therefore run the application with no further changes, and the homepage loads correctly. Dependency injection brings with it many advantages that make applications easier to maintain and evolve. Benefits include promoting the loose coupling of components and the use of abstractions, both of which ensure that low-level code changes don't propagate up to higher-level code. Using dependency injection also supports improved testing by allowing unit tests to inject mock or fake dependencies, and it helps us to improve the readability and the cleanliness of our code. Remember that amazing weather forecaster we created earlier? It also implemented the iWeather Forecaster interface. Now that we're using dependency injection, it's easy for us to swap out the implementation type resolved at runtime simply by updating the service registration. We can change the implementation type for this service registration, and we don't need to touch the index model because it still depends on an iWeather Forecaster abstraction. I'll start the application by pressing F5. When the iWeather Forecaster is resolved, the amazing Weather Forecaster service is now injected into the index model for the home page. I can refresh this page several times, and the weather remains sunny every time. A single change like this to our service registration conveniently takes effect throughout the whole application for any code depending on iWeather Forecaster from the container. A second benefit is that the index model is now easier to test. This code fails to compile because the index model no longer has a default parameterless constructor. To fix these tests, let's create some fake weather forecaster implementations for use during testing. We could of course use a mocking framework here, but because the interface is so simple, we can implement it ourselves. The first implementation will return a fixed weather result where the summary always returns sun as its value. We can copy this fake and make one that always returns rain as its summary value. For the test that asserts on the sunny description, we can now pass in a new instance of our sun forecaster fake. We also need an iLogger argument for this constructor. Fortunately, Microsoft has us covered, and we can use a null logger of index model here, accessing the static instance. This test now compiles. We can repeat this for the rain test, passing in the rain forecaster fake. I will now run the test from the test menu, and they both pass. Due to our changes, we're now able to successfully run these unit tests and adequately test the logic of the index model. Because of our refactoring, we can manually provide dependencies using fakes, mocks, or stubs during testing. This is a valuable advantage of inverting control with constructor injection, combined with depending on abstractions rather than concrete implementations. In the next module, we'll learn more about the Microsoft Dependency Injection Container. In this module, I'll introduce the Microsoft Dependency Injection Container, which is the backbone of all ASP.NET Core applications. You'll learn how this is used by ASP.NET Core to activate framework components. And I'll discuss the types of objects which should be registered with the container, as well as those which shouldn't. Finally, you'll learn about service lifetimes, how these affect the services managed by the container, and how you should choose between them. Let's briefly focus on the ASP.NET Core request lifecycle. When an ASP.NET Core application starts, the host binds the in-process Kestrel web server to some ports. Clients can then send HTTP requests to these ports which Kestrel accepts and processes. Kestrel parses the HTTP request message and produces an HTTP context representing the state of the request. At this point, a scope is created for the current request. The HTTP context is passed into ASP.NET Core, which processes it via the configured application pipeline. The pipeline includes several middleware components, and then the final endpoint, which will produce the response, in our case, the endpoint for the Razor page. Services that are required in order to activate components such as the Razor page handler are then resolved from this scope. By resolving services from the scope, rather than from the root iService provider, instances of scope services are only shared across the current HTTP request. ASP.NET Core ships with its own built-in dependency injection container, which it uses to resolve the services it needs during the request lifecycle. All framework services, for example, logging, configuration, and routing, use dependency injection, and they are registered with the dependency injection container when the application host is built. Internally, the ASP.NET Core framework provides the dependencies required when activating framework components, such as controllers and Razor pages. The Microsoft container is packaged into its own assembly in the Microsoft.extensions.dependency injection namespace. In the default ASP.NET Core templates, the project file for applications specifies the use of the Web SDK. The Web SDK includes an implicit reference to the ASP.NET Core shared framework, packaged as Microsoft.ASP.NET Core.app. This app package references required libraries such as dependency injection. A dependency injection container, sometimes referred to as an inversion of control or IOC container, is a software component that manages the instantiation and configuration of objects. A dependency injection container is not a requirement to apply the dependency injection pattern, but as your application grows, using one can greatly simplify the management of dependencies, including their lifetimes. Services are registered with the container at startup and resolved from the container at runtime whenever they're required. The container is responsible for creating and disposing of instances of required services, maintaining them for a specified lifetime. There are two primary interfaces that we code against when using the Microsoft Dependency Injection container. The iService collection interface defines a contract for registering and configuring a collection of service descriptors. From the iService collection, we will build an iService provider which defines a mechanism for resolving a service at runtime.